Recording. Full screen. It's kind of a shame that this board somehow doesn't come down all the way, but there well. Okay, very cool. Let me know if anything goes off the page, like in this lower section over here. Alrighty, wonderful. So yeah, today we're going to talk a little bit about optimal control, dynamic programming, and then we're going to go ahead and yeah, finally discuss RL. That's what Tarun will be covering today. Okay, so with that, we could sort of talk about a little bit of an overview of what optimal control is. Optimal control. So we've actually been doing this like a whole bunch in class already, right? We did things like, we had MPC, we had control Lyapunov functions, control barrier functions. We're now doing many, many more, right? So all that optimal control is it's really, we're trying to solve some sort of optimization problem to figure out the best input to our system, right? So we solve an optimization to get the best input. Okay. And this is pretty good in general, right? But what we might want to do is, these techniques are all, I don't know, somewhat dispersed, you could say, from each other, right? It would be kind of nice if we had like a good framework for solving a lot of these problems in general, okay? So we want to develop a framework for solving optimal control problems. All right. So we're going to talk about one really, really general class of optimal control problems today. It's not going to fit everything, but it's really going to cover quite a few. And yeah, so we're going to go ahead and develop like all these techniques that will apply to this very general class of optimal control problems. And we'll see how they sort of pop up again in reinforcement learning later on. Alrighty, great. So let's sort of talk about what that class is, okay? So our class of optimal control. So let's imagine that we have some discrete time system, and that system is going to have the form x at time k plus 1 is equal to some function of the state of xk and the input at time k, right? So that's our state vector, and that's our input vector, right? So this is just telling us, okay, we have our state at time k. When we plug in this input to our system at time k, that'll go ahead and put us up to xk plus 1, right? Our state at the next time step, all right? So here's what we want to do. For some finite time n, we want to identify the best inputs to the system. All right? So we sort of call this n a couple of different things, right? In MPC, we called it the horizon, for example. It's just really this time of interest that we have in our system that thinks about, how far ahead this optimal control problem is actually looking, right? So what does this actually come down to solving, right? If we want to identify the best inputs to the system for these n time steps, what we actually want to solve for is an optimal sequence of inputs, right? Optimal sequence of inputs. So what we're going to try and identify are these optimal U0, U1, all the way up until UN minus 1 that give our system optimal behavior, okay? All right, so for this type of system, right, we're going to have a general type of cost function. So general type of cost function. And this is going to be a type of cost function that really shows up a lot. Hey, Jackson. So it's going to look a little bit familiar to what we talked about in MPC. It's also going to apply to other types of optimal control problems like LQR, all these other great things, all right? So what's our general cost function for this n-step optimal control problem? Well, we say our cost is going to be J equals LFXN. I'm just going to write this out at first, and then we'll talk about what these little terms mean afterwards. So that's sum k equals 0 up to n minus 1, L of xk, uk. Okay? So what we want to do is we want to try and optimize this sort of, cost function in our optimal control problems, all right? So this first term that we have up here, LF of xn, this doesn't stand for a Lie derivative. There's a lot of conflicting notation, unfortunately. But what this stands for is something called a terminal cost. Terminal cost, okay? So it tells us about the cost associated with our final state, xn, right? Where we sort of end up after these n steps of interest, okay? And what about this other term over here? So inside the sum, we have this term called the stage cost. And that doesn't tell us about our final state, but it tells us about the cost associated with everything along the way, right? So this tells us about our costs associated with states along the way. And our inputs. Okay, so if you're just coming in, let me just summarize real quick what we've talked about. So essentially what we've said is that, we want to sort of generalize these optimal control problems, right? So we have discrete time systems, they kind of look like this, and we want to determine an optimal sequence of inputs over n steps for these systems, all right? So what we've said is that, all right, this sort of cost function will model these situations pretty well. We have some cost associated with our final state, and then we're adding up all these costs along the way that tell us how our system is doing as we proceed to that final state, okay? So what are we doing in this case? If we're trying to optimize for a sequence of inputs, right, we want to solve the following optimization problem, okay? So we want our optimal sequence, u0 star, u1 star, all the way up to un minus 1 star, equals argmin over all possible sequences of inputs, right? u0, u1, un minus 1 of this cost function, L of xn plus sum k equals 0 to n minus 1, L of xk uk. All right? So do we have any questions about, how we got to this sort of point in our process, so like how we've arrived at that?
That's my question is how exactly is the terminal cost different from the stage cost? Is terminal cost, because like it seems like if you're compounding the cost of every time such not screw entire.
Yeah. So it's more of a notational thing. So the terminal cost is really something that just penalizes like how far away our final state is from where we'd like to be at the end. So it does have input as well. Yeah. So since we're at that final state, we're no longer applying an input to the system. We're just sort of there. So yeah, we kind of differentiate about it. Yeah, good point. Any other questions? There we go. Cool. Okay, so it turns out that this is actually a really hard problem to solve, right? Really hard to solve. What we're essentially asking is to optimize over this entire, could be really long sequence of n inputs in this case, over this potentially really complicated cost function, right? So what we want to do now is we want to come up with a way of breaking it up into smaller and solvable problems. Okay, so how do we do this? Well, we have this technique called dynamic programming that allows us to do exactly that, all right? So we have this entire optimization problem, and we're going to say, hey, instead of taking this whole thing head on at once, what if instead of solving this huge optimization problem over these n time steps, we could solve like n smaller optimization problems, all right? So here's what we're going to do. We're first going to define something called the optimal cost to go. Cost to go, okay? What this is we're going to imagine we've already taken, let's say, I optimal steps. What that optimal cost to go is it's the remaining optimal cost, all right? So how much we have left, remaining optimal cost from I all the way up until n, okay? So we're going to denote this with this little j optimal for optimal cost to go. And then we're going to have I. So our optimal cost to go from step I. And we're going to define this to be the minimum over our remaining sequence of inputs, right? ui to un minus 1 of L of xn plus now our sum's not going to start from 0, but it's going to start from I, right? K equals I up to n minus 1 L of xk uk. Okay, so now we're sort of honing in our focus on this cost function a little bit. We're saying instead of looking at this whole thing, we're going to look at our optimal cost to go from state I. All right. So now we're going to do something a little kind of funny here. We're going to try and rewrite this optimization problem over a sequence as an optimization problem over a single one of these variables, right? We're just going to try and focus on optimizing for ui, right? Let's try and optimize for ui. How are we going to do that? Well, the first thing that we're going to do is we're going to rearrange some of the terms in this, all right? I'm going to try and pull out the first term out of this sum over here, okay? So I'm going to pull out L of xi ui. And now my sum is going to be from k equals I plus 1 up to n minus 1 L of xk uk. Okay? And I'm just going to rearrange some things. Un minus 1 L of xi ui plus L of xn plus this sum k equals I plus 1 up to n minus 1 L of xk uk. Okay, so now I have a question for you guys. What is this term over here in terms of these things that we've discussed so far? Does that look familiar? Yeah. Right, that's J0 I plus 1. Okay, so what we see is that using this sort of expression, right, we can actually figure out a recursive formula for our optimal cost to go. So min over ui, un minus 1, L of xi ui plus our ji optimal plus 1 of xi plus 1. All right. And we're going to assume we take optimal inputs and all those sorts of things from there. So we're just going to say it just depends on I plus 1. All right. But now here's another question. All right. What is xi plus 1? Do we have anything at our disposal to try and express that in terms of xi and ui? What can we do? Thoughts?
Yeah, it's the dynamics.
Right, that's our dynamics equation. So we can express that as f of xi ui, right? So what we see is that we can actually express this problem of xi ui plus ji plus 1 optimal of f of xi ui. Okay? So we've gone from optimizing over this entire sequence to just optimizing over a single variable, right? Yeah, what's up, Jackson?
Yeah, that makes sense. But then like the dynamics equation doesn't really work a lot of times in what we've seen, and so we have to do like this better estimate, like state estimation. Like, does all of this
Yeah, yeah.
like, work?
Yeah, so all of this really does depend on our dynamics working, right? So what we could do in practice is that there's another formulation of this called stochastic dynamic programming. And what we could do in that case is we say, we imagine our system is noisy. It's noisy. And we augment our dynamics with this extra term, with x, xk, uk, wk. This is a disturbance term. And that can essentially model the inaccuracy in our dynamics. So as long as we're able to model that disturbance with some sort of probabilistic method, right? We have some sort of distribution for it, then we'll actually be able to account for that in what we're doing. Yeah, that's a great question. Right, so you can figure that out with your Kalman filter or doing some sort of statistical estimation. Yeah. All right, yeah, great question. So this equation over here is actually a really famous equation called the Bellman equation, all right? So it's named after this very, very famous American control theorist. He's called Richard Bellman. And if you guys haven't heard of him, I think he had the record for like shortest PhD ever. I think he did in like 3 months, which is kind of nuts. So yeah, imagine that. But yeah, sorry, did you have another question, Jackson?
Yeah, like if the noise is like, like centered at 0,
Yeah.
then does this change anything?
It doesn't actually change anything. So what we do in that case is we take the expected value of our cost function instead, and that'll sort of zero out. So it might impact some sort of formula for the optimal cost to go if you get that in a closed form, but your actual solution to the problem should be the same. Yeah, great question. Okay, so we have this thing called the Bellman equation, right? And it tells us we could split up this optimization problem into a bunch of smaller steps. So what we're going to do in dynamic programming is we know what our optimal cost to go at state n is, right? That's just going to be LF of xn, right? Simple formula, we don't have to perform any sort of optimization over there. We're already at our final state, right? So if once we have that, we're going to work back and we're going to say Jn minus 1 optimal is going to be, according to our Bellman equation, it's going to be L of xn minus 1, un minus 1 plus ji plus 1, which in this case is Jn optimal. It's going to be LF of xn minus 1, un minus 1, right? We're just going ahead and plugging that guy in there. Okay, and then we solve for un minus 1, And then we continue the process, right? Jn minus 2 optimal equals blah, 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 all the way until we get down to our 0 term, right? And at that point, we'll have identified our entire optimal sequence. Entire optimal input sequence. Okay, so what we're doing is we're starting all the way with our final term that doesn't depend on any inputs, no optimizations needed, right? We step back to our first term, we determine our optimal state, then we go back one more, all the way until we reach the 0 term, all right? And at that point, we'll have gotten all of our optimal inputs, U0 through UN minus 1. Okay, so that outlines this procedure of dynamic programming. Do we have any questions, or how are we doing so far on this? What do you think? Yeah.
For J0
Mhm.
are we not missing the J0 minus 1? Then equation that we found.
So for J0n, what happens if we look at this sum is that if K starts at what you call it, N in this case, and we're summing, yeah, that sum just disappears. Yeah.
I think something could be wrong in the dynamic programming.
Mhm.
The first stage is, so JN0.
Yeah.
Is that saying find the best ending position?
Yeah, so Jn0 is going to say, imagine we've taken an optimal sequence of inputs up until this point. We're now at this state N.
Oh, and
Okay. What's our cost? Yeah.
Sure. But at the Jn minus 1 0 stage,
Mhm.
I feel like what you wrote is incomplete.
Oh, there should be a minimum over UN minus 1.
But even still, don't we need to account for all possible x n minus 1s, all possible?
Right. So what we're going to do in this case is we're going to solve for UN minus 1 as a function of xn minus 1. So when we perform that optimization, it's actually going to be able to deal with all possible states there.
Okay, so we find, but we don't know what x n minus 1 is. So
Right.
We can't continue and perform this optimization.
So that's what the whole idea of including this min is, right? So we sort of abstract this idea of what these states are. We assume that they're optimal, and then we just get an arbitrary formula for u in terms of those states. And then all the way at the end, by working our way backwards, we'll have optimal formulas in terms of these arbitrary states, right? So then when we actually go and apply them, those optimal states will sort of propagate back forwards through this.
So are we looping through all x n minus 1 and u n minus 1, or are we just looping through all possible u n minus 1?
We're just optimizing over UN minus 1. Yeah.
And then the input will inform our states.
Mhm.
Because it must follow the dynamic.
That's right.
Okay.
Yeah. Great. Yeah,
If we don't know what x of n minus 1 is in any of these situations,
that's right.
then how do we optimize for that if we don't know the data for x?
Yeah, so we just treat it like a symbolic variable, like an unknown. So I'll show you guys, I think this will make more sense once we do a more concrete example, but we're going to end up finding UN minus 1 as a function of that unknown, and then it'll hold for all possible values of that. Yeah. Okay, great. So let's jump into an example over here. I think this will help clear up some of the questions that we have about this. All right. So let's say, consider the scalar discrete time system. And this is the first example problem that's on the worksheet over here. Is there anyone that wanted a paper copy of the worksheet that didn't get one? All right. So we're going to say, consider the scalar discrete time system. Xk plus 1 equals a times xk plus b times uk. All right. So xk, uk, they're just scalars. We're going to keep it nice and simple. All right. Let's say we want to minimize the following cost function. Okay. Xn squared plus some k equals 0 up to n minus 1 of xk squared plus uk squared. All right. So we're going to try and figure out un minus 1. We're just going to do the first step, all right, with dynamic programming. All right, so a good first step in this is to try and identify our terminal cost, right, LF of xn, and our stage cost. So our terminal and our stage L of xk, uk. Okay, so what would those be in this case? What's our terminal cost? LF of xn going to be? So that's going to come from this expression. What do we think?
Xn squared.
Xn squared, right? And then our stage cost is going to be right. We're just going to pull it directly out of that sum. Xk squared plus UK squared. All right. So our terminal came from right there. Then our stage came from right over there. All right. Okay. So now what we could do is we can start with our terminal cost. All right. So based off of that discussion above, right, we know our optimal cost to go starting from state n, just going to be our terminal cost, right? LF of xn, which in this case is xn squared. All right. So now what we're going to do is we're going to go one step back. Okay. So our optimal cost to go at time n minus 1 going to be the minimum over our input at time n minus 1 of our stage cost at that state, minus 1, un minus 1, plus our optimal cost to go at the next state. Okay, this is just based off of that Bellman equation. All right, so let's substitute our terms in for this particular problem, okay? So this is going to be the minimum over un minus 1. L in this case is going to be xn minus 1 squared plus un minus 1 squared. And then we're going to add on our optimal cost to go at time n, which is going to be xn squared. Okay, so what do we do at this stage in the problem to write everything in terms of un minus 1? What do we do? Right, in terms of un minus 1. So these two terms are already good. What are we going to do with this xn over here? Use the dynamics, right? So we said this is our system dynamics, right? AK plus BUK. All right. So this is going to be A times xn minus 1 plus B times un minus 1 squared. Okay. So now this is a minimization purely over un minus 1. Let's just expand this out. Squared plus A squared xn minus 1 squared plus 2AB xn minus 1 un minus 1 plus B squared un minus 1 squared. Okay. So how do we minimize this function with respect to un minus 1? What do we do? It's a quadratic function, right? Oh, I'm going off the bottom of the page. So all that we need to do to minimize this, we could just take its derivative and set it equal to 0, right? Okay. So this is jn minus 1 optimal. du n minus 1. And what's that going to give us in this case? So we're going from this function up here. We're taking its partial derivative with respect to un minus 1. Mm-hmm. Okay. And we should have. Yeah, great. And minus 1 equals 0. Okay. So at this point, all we need to do is solve for un minus 1, right? So then let's just group our terms together here. We could cancel out all of these 2's from this expression, right? And then we'll have a un minus 1 times 1 plus b squared plus ab times xn minus 1 is equal to 0. And that tells us that un minus 1 is equal to minus 1 plus b squared inverse ab xn minus 1. Okay, so that gives us our optimal input to the system at time un minus 1. And we see it's entirely in terms of that variable xn minus 1 that we don't yet know. Okay, does that make sense? All right, great. So something interesting to note over here is that this is just state feedback, right? All that we've seen after this entire optimization problem is that this thing will just boil down to a simple, we have a constant k, our gain, multiplied by our state vector x at that particular point, all right? We can actually prove if we keep going in this case that that sort of relationship is going to hold throughout this entire thing. So this is actually a simple version of something called an LQR controller. That's what it is. So in your homework, you guys are actually going to derive the full version of this LQR controller, okay? So we're going to bump it up to the vector case, make our cost function a little bit more general, and you're going to see that all LQR is really just a fancy version of state feedback with a couple extra tricks up its sleeve, okay? All right, so once we have this UN minus one, what we want to do is we can go ahead and plug it back into JN minus one optimal, and that'll calculate a closed form version of JN minus one optimal. And we can continue this optimization going all the way down until we've identified our optimization is zero. Yes, Jackson.
How is this different from what we did like earlier? I think it was like the second homework or something where we were optimizing over like the cost function over.
Right, yeah. So MPC is really something that's very, very closely tied to what we're doing with dynamic programming here, okay? So what we said in MPC is we're just trying to optimize something over some horizon, and that's essentially what we're doing in this case. Here, we're just looking for a closed form solution for it. In MPC, we just threw it at a black box optimizer, yeah. So in this case, this is something that's only really tractable as long as you have like, linear dynamics. Once you have nonlinear, it's kind of hard to solve, and that's where MPC comes in. Yeah, great question. All right, so if there's no other questions, I'll hand it over to Tarun. We'll talk about the miracles of reinforcement learning.
You're excellent. You're excellent. Control is something different, guys. Wait, is this gonna project my Zoom screen?
Yeah, sure.
Yeah. Whoa, what? I just fell. Okay. Sorry, let me. Oh, can you give me? Actually, maybe I can. Yeah, I can.
Make sure you're not joining with the audio in here, because otherwise it'll
Yeah.
clash with the mic.
Oh, it's on the screen.
Yeah. So I'm going to mute and exit full screen. Do you want to just write on mine?
I can do that, right? Just give me co-host. Yeah. I don't know where your mouse is.
State
Oh,
estimation.
I just. Oh,
there
there.
it is. There it is. Oh wait, it should be under a share screen, right?
Oh, I was gonna make myself co-host.
I don't approve.
I have to prove it over here. Oh, actually, this is too complicated. I will just. God damn it.
Oh no, I think that's the Zoom. That's exit Zoom.
Oh. Not clicking X.
Yeah.
Oh, I think we have to exit out of this thing then.
Oh, shoot. Oh my god.
Oh, you just said yes.
You're not getting host. Oh, wait, it showed up on this window. All participants. All right, that's a wrap. View.
Yay.
Screen. All right. Nice.
Okay.
Actually being the host twice.
Yay. Okay. So thank you for that optimal control intro. That was really cool. So now we're going to talk about the ideas behind reinforcement learning and where it kind of fits with this whole idea. Reinforcement, so optimal control gets us to this closed form solution for what we want our inputs to be. But sometimes we have a much more complex problem. We don't really know what our transition probabilities or cost functions might be. And we want to test behaviors out and reinforce good behaviors. So reward the positive experiences and punish the wrong ones so that at any state, we know exactly what we want to do to get our maximal reward. So to that idea, we have a few different concepts within reinforcement learning that we have to talk about first. So RL is we have no closed form solution necessarily. Unlike OC, instead we want to experiment, find a good behavior based on states,
and essentially find the best actions. So, for example, if you're considering walking, it might be difficult to get your cheetah to be moving forward or your bipedal robot to be moving forward, but you want to test different behaviors out, and based on the current position of the robot's legs and where it is at the moment, you want to find some kind of action that you want to take that gets it moving in the direction you want it to go. So the few different ideas we want to implement here is the idea of a policy. This is the action we should take at any arbitrary state. At some state. And we want to find the optimal policy. Find best actions. So, which is the optimal policy? There are a few different ways that this could end up happening. And one of the first ones that we're going to talk about is this idea of Q learning. So Q values are pairs of state action. So I'm going to call them state action pairs. So if I'm at some position and I conduct some action, what is the Q or the quality value that results from it? So what reward do I get for this pair? This works very well with certain kinds of functions. You might have some kind of Q function based on your state, and you want to find what the reward is for the action that you take at that state. We talked about the Bellman equation in the context of optimal control. There is an analogous Bellman equation in the context of Q learning where you take some sample, you perform some experiment. So you're at some state and you do an action. What is the reward that we get from that action? Start at S, perform action. So we get the sample is equal to the reward that we get for that action. S, we perform action A, and let's say we end up at state S prime. Plus gamma, which is our discount factor. This is usually some fraction of value in order to ensure that we're preferring sooner rewards. So future rewards that we're going to get after we transition to state S prime are discounted. So the reward that we get for this particular sample is a little bit lower because the future rewards are punished a little bit more. So some discount factor times the best action that we can take from S prime. That's A prime, Q of S prime, A prime. Best action from S prime. Okay, so does anyone have any questions about the sample that we're taking? We're performing some experiment from a current state. We do an action and we record the sample, which is the reward we get from that action plus future rewards that we're going to get multiplied by discount factor. When we want to update what our Q value is for a particular state action pair, we're going to perform a ton of different experiments. So we're going to start at some state, we're going to perform this action, and we're going to do it multiple different times. We might get different rewards each time just because the result of our action might not be deterministic. We don't have any probability distribution of what our final state is going to be from this present state. So what we instead do is perform something called temporal difference learning, or exponential updates, moving average updates over what our Q value is for this state action pair. So the action isn't deterministic. So we update recorded Q value with samples. So the Q value for our state action pair is going to equal 1 minus alpha times our current Q value, plus alpha times the sample value. And as you perform more and more experiments, you're probably going to reduce your alpha over time. With data. Alpha is what we call our learning rate. So how fast we want our policy to update new values. Okay, any question on the concept of Q learning?
So,
Yeah.
go ahead. I guess the main thing is that, so if it's our rate of learning, I guess, is the idea here that you might like overfit or something? If your alpha is too large, you have a lot of data, or?
Well, alpha is updated with every sample.
Yeah.
So if your alpha is really big, you want to prioritize the results you're getting from your new sample more than you want to prioritize the old data that you've already collected.
Yeah.
But over time, you're going to collect a lot more data.
Yeah.
And you want each new sample to influence your result a little bit less.
Okay.
So you might reduce your alpha over time.
Okay.
Is in practice, this is only good on like pretty small spaces.
Yeah, so the homework has some information about Q values. You might have a Q function instead, dependent on your current state. And this particular brand of iteration that we're going to do is going to be done on discrete spaces as well. With continuous spaces, we'll talk a little bit more about in a little bit. Yeah.
So it seems like we're assuming that the underlying reward is fixed.
Mhm.
Because otherwise, I don't see how we can converge to be like the true Q value. Because in that line that you just wrote, it seems like we're trying to find the best Q.
Yeah.
As a mapping, right?
Yeah.
So we're trying to find what it actually is. So the assumption, I guess, like my question is, are we assuming anything about our environment?
So realistically, you're not going to be able to find some deterministic function for some state action pair. Instead, we might use some kind of deep learning with deep Q learning. So plug in our current state and figure out whatever action that we might need to get the best outcome. And this is, we find a policy instead. So yes, in this case, we're trying to find some Q value for this particular state action pair. But that Q value is going to iterate over time, and we expect that this to converge with a given environment, or converge to some average at least, even if there is some noise around it. So we want expected reward for a particular action to be the highest. All right, so let's try an example with some kind of deterministic grid world. Sorry, I made a diagram, but didn't end up putting it in the document. Let me draw it out right now. So let's say we have this little grid. The top right square as an exit of, if we exit from the top right square, we get a reward of 10. And we start from the top left. We're going to call this square 1, 1. I'm going to call this 3U1. And we have a little Pac-Man who starts in 1, 1. And we perform a few different episodes of training. So we do different actions at each space. And let's say that for this particular brand of Q learning, let's say we're going to update, we're going to keep going right from 1, 1. And we're going to try to find what our Q value is for 1, 1 going right. In our first episode of training, we go right from 1, 1 as usual. Then we go right again. We end up at 3, 1, and we exit with a reward of 10. So let's figure out what this particular sample is. So the sample is going to equal the reward plus the discount factor times the future rewards. So at the exit, we just get a reward of plus 10. So the sample over here is going to be plus 10. At the state before that, we're going to do the reward for transition. So the transition reward for this going right is 0, plus the discount factor gamma times the reward for the exit, which is 10. And we're going to say gamma equals 0.1. So this is going to equal 1. And finally, at our starting position, we have a reward for transition, which is 0. plus our discount factor gamma, gamma times 1. So this is going to end up with 0.1. We could do a similar thing over here. So we have plus 10. We get 0 plus 0.1 times 10, which is 1. 0 plus 0.1 times 1, 0.1. 0.1 times 0.1, 0.01, and then this will have 0.00. And the last episode, we go right. We attempt to go right again, but we end up going down. We keep going right, and then we exit. Same thing, we have about 4 different states here, and we get a reward of 0.001 for that particular episode of trade. When we perform temporal difference learning, we start with the first episode. After episode 1, we have a reward of plus 0.1 at the end of this. In episode 2, we want to update this value with our learning rate. So we're going to use our learning rate, 1 minus alpha times episode 1 plus alpha times the reward that we get after episode 2, which is 0.5. 1 minus 0.5. The reward from episode 1 was 0.1 plus 0.5 times the reward for episode 2, which we got was 0.001. And then after episode 3, we do the same kind of thing. We have 1 minus alpha times the reward after episode 2 plus alpha times the reward of episode 3. And we keep updating this value. We might reduce alpha as time goes on. We keep performing episodes of training where we experiment with our pacman in the squared world. We start from 1, we go right, and we let it go until it arrives at our goal. And we see what our Q value is, or converges to, at the end of it. In this particular case, I was only performing Q iteration on 1 going right. And for the rest of the world, I kept a uniform policy of where it's moving, and I wasn't calculating the updated Q values for the other states and action pairs. Realistically, you probably would perform Q value updates for everything else as well. In this example, we were just taking certain samples and performing Q updates over there to give you an idea of what Q values are. Yeah.
Can you explain the difference between time difference, temporal difference learning, and Q learning?
So temporal difference learning is this idea of updating samples over time.
Okay.
So it's still Q learning. You're learning Q values. You're just taking these samples over time and updating it.
So can you scroll back down? So it sounds like.
Wait, wait.
So for episode 2, you're saying we start at episode 1, or yeah?
Yeah,
can you
so-
give the reasoning behind that?
So yeah, so this is 1 minus alpha times the Q value we've had so far.
Yeah.
So this is our current estimate.
Why is that not E2?
E2. So maybe I should change this to be like alpha times sample 2. And then this one I'll make sample 3. And this is not the result of episode 1, but our current Q value after episode 1.
Oh, each episode is starting from the same place, right?
Yeah.
But they have different actions.
Different outcomes that result from these actions, yeah.
Okay.
So it's our current Q estimate that gets updated with our samples. And we're updating over time. So this example is a little bit bare bones. It just gives you the idea of what Q values are and how we might go about updating them. There is a little bit of black boxing of what's happening in the other states and the other actions. But the idea is that we have this Q value and these actions that we're taking, and we're updating our Q values over time. Okay, so The other option, instead of performing queue updates, we perform policy updates. So we might have some kind of function, or instead of policy learning. So we might have some function of our current state. And this might be a vector, might be, 25, 30 units long. Depending on the kind of robot that you're working with. And it's going to define where you are at the moment. Current state, which is a vector. Your robot, your humanoid will have a different state vector than, say, a cheetah. But essentially, you're going to have to describe where you are at the moment. And you'll have a reward function. This tells you how good your state is. So we have these two components, and these two ideas are the important parts of what we need to construct some algorithm that tells us what to do from this point. So we feed in a function, our current state. Some algorithm. This will usually be some kind of neural network, maybe. And the reward function. The idea behind a neural network is that you're trying to minimize cost or maximize reward. So we're going to feed in this reward function and try to maximize the reward, and the output is going to be some kind of action. So we're going to train this network based on our current state and what our reward function is to give us an action that maximizes our reward. As a result, you're not learning Q values or learning what the state action pair is and what the reward is for each state action pair, and then maximizing over actions. You're just feeding in the state directly, you're feeding in your reward function, and you're getting an action that's probably best.
Is the reward function related to the Q values at all?
Yeah, so the Q values are estimating your rewards for particular state action combinations. In this case, our reward might be what is best for the robot to do. So we'll construct a reward function in a second for walking versus standing versus like juggling or something. Your reward functions might be different, but it's going to be some kind of function that tells you how well you're doing what you want to do. Okay, so let's say we want to perform reinforcement learning and find out what the best actions are for this cheetah robot to walk forward. Let's start with finding some kind of observation vector. So this is our feature vector. What can we do to represent the current state of our robot? What attributes of it can we use? Yeah. Yeah, so we might have like joint. Yeah, positions and angles. Say foot contacts. Oh, do you have something?
I was gonna say, like, you define like some center or something, it's like the position of that center.
Yeah, center of mass. And then I'm going to add one thing, which is like velocities, which might be like linear or angular. And the real life feature vector for this cheetah in Majoko does have a combination of these particular features. It's an R18, I think. So it's 18 units long and with some combination of these ideas. And now let's say we want to, now that we have our state, we want to construct some kind of reward function for this learning algorithm. We want this cheetah to walk forward. So we want to construct some kind of forward moving reward function while also punishing larger movements so that you don't lose balance or you're not expending too much energy on these movements, etc. So these are two different conflicting things where you want to be moving forward, but you don't want to be expending too much energy. So how can we construct this reward function? Actually, it's 3 p.m., so let me give this to you. So moving forward will be like, say, distance traveled. Maybe normalized by time between measurements. And then we want to punish by subtracting, let's say, the magnitude of the action. So the reward, you do plus distance minus the magnitude of the action. So now that we have this reward function as feature vector, we might feed it into some kind of neural network. This is a simplification of things. This gets significantly more complex much more quickly. But now that you have some reward function and you have some current state, you might feed in this reward. You might feed in the current state along with this cost or reward, and output the action that minimizes cost / maximizes reward for you.
You're gonna make the neural numbers.
Are we good training networks?
You're gonna train it for a lot.
What's the simulator?
Image of it. Wait, a half a cheetah?
Yeah, that's this one.
Oh, 191.
Say it's two.
Ooh, we tried the 3D ones. They collab was not happy.
I think the whole training time for 3 months would take you out until 5 seconds, so.
He said like, you could make like a million of these things go at the same time.
They have very nice servers.
Um,
We have fewer
Yeah, Jim is really nice. We also have to accommodate for everyone who doesn't have a GPU.
Is this?
So this will run on the cloud, yeah.
Great.
Okay, cool. Maybe I should end the meeting, but we can keep talking if you guys are interested.
Oh, we did it.
Yeah. You want me to do, I think they have like a premium one you have to pay for, but they have some. That's what we're using, yeah. I think you need to use, you can get exit for free.
Okay, should I just end it?
You have to explicitly call the GPU